When we drew Lewis structures, the shape of the molecule was not communicated in that structure. All we were going for is what is connected to what are the formal charges, where are the electrons in this molecule. Now we can take what we know and put together a molecular geometry. We're going to use something called valence shell electron pair repulsion theory, which usually gets called VSEPR, even though it's spelled VSEPR, right? It's valence shell electron pair repulsion theory is just a lot to say. So we're going to call it VSEPR. You can call it VSEPR if you would like. The principle behind this theory is that electron groups repel each other. So, nothing terribly groundbreaking. Negative charges repel each other. And they spread out as far as they possibly can. The thing that makes this a little harder to see on paper is that they have all of 3D space to spread out in. So when they spread out as far as possible, it's in 3D space, and that affects the geometry around a specific atom in a molecule. So the steps that you will use for sketching VSEPR geometries: first, draw the Lewis structure and make sure you have the best one. The second is to determine the steric number, which we abbreviate SN, around the central atom, and use it to arrange a basic geometry, which we also call the electron geometry. So when I say steric number, what I mean exactly by this is the number of bonded atoms and the number of lone pairs. So really just the number of things around this central atom. The steric number and basic geometry, that steric number is what you will use to put things as far apart as possible. And we're going to draw a lot of fun 3D pictures with this. For now, I've got names, and some of these are going to sound familiar to you, but this is where we're starting. So if the steric number is 2, the basic geometry or the electron geometry is linear. For steric number of 3, it's called trigonal planar. Steric number of 4 is tetrahedral. A steric number of 5 is trigonal bipyramidal, and a steric number of 6 is octahedral. Now this is just the basic organization of things. When we're organizing these things, we might need to consider the placement of atoms in special cases. And really, it's just for steric number equals 5. So steric number equals 5 is a special case. It has a rule called Bent's rule. And this rule says that if you have a more electronegative atom, which is really code for a smaller atom, you put it in something called an axial position, and the less electronegative atom, which is just code for a larger atom, you put in an equatorial position. And what you will see when we draw this picture is that axial positions have less space, and equatorial positions have more space. So you put the smaller thing in the space with less space. When we do this, you do need to think about how you would deal with a lone pair. And I will just tell you, a lone pair is considered large. So if you're putting a lone pair on, you would put it in a place where there is more space, which would be an equatorial position. The next thing that we look at are adjustments to bond angles. So when we put together our basic ideal structure, as far apart as they can get in 3D space, you can figure out the angles. And I will give you the angles. Once we start having real atoms or lone pairs instead of atoms in those spaces, the angles will change a little bit because some things repel each other more than others. We use this repulsion order that I have listed to help decide what the repulsions would be and how it would affect the angles. So what this is saying is that two lone pairs would repel each other more than a lone pair and a bonding pair. So, the two lone pairs, if they have to interact with each other, they're going to push harder away from each other than a lone pair would push away from a bonding pair. And that would push away from each other more than a bonding pair and a bonding pair. And this, right, we'll see it in action where it will make a little more sense. Then the last thing, if we are giving a name to the shape of our final molecule, we name it based on the coordination number. So the names that were given earlier, that's for the electron geometry, the basic format in which we are putting atoms around the central atom. But when we're looking at the final structure and the final shape, we only use the number of attached atoms. So we ignore the lone pairs and just use the atoms that are connected to get the name of that shape.